So this is a sample problem about how you can figure out a lot of information without much given. In this particular case, we're going to use it to figure out the mass of the sun, just using the time that the Earth takes to rotate and the distance of the Earth from the sun. This will work in any case where you have a center object that's much more massive than those that are orbiting it, which normally happens in things like satellites around the Earth, planets around stars and other things around the center of the galaxy. So pretty useful. So in this case, we're going to use the Earth. The Earth is on average about 150 million kilometers, or 1.496 times 10 to the 11th meters away from the sun. Not exactly, because it's a slightly elliptical path, but that's the average. Thinking about leap years, overall it takes about 365.25 days for the Earth to completely go around the sun. From this, we can figure out the Earth's speed. So the velocity of something going in a circular path is a circumference divided by time. That's simply another way to find distance over time. And so I used 2 pi times r, got that down there to get circumference. To find the time, I converted days to seconds. It's important that you do show your steps if you do that on a test. That's down there. Move those up, and I got around 30,000 meters per second. That's fast, but that's really how fast we're going. So to find the next step to find the mass of the sun is to find the acceleration of the Earth around the sun. In other words, the acceleration caused by the sun of a certain mass. So to use that, I can use my centripetal acceleration formula. I know the velocity because I got that. I know the radius. Now, in a way, we could use this and combine these things to get one equation, and there are ways to do that, which we'll talk about. But for right now, we're going to take it in a few steps. So the centripetal acceleration is 0.00593 meters per second squared, or 5.93 times 10 to the negative third meters per second squared. So that's a small acceleration, which seems odd, but we're very far away from the sun. And that's in terms of meters per second squared. So that acceleration we can use using the equation we've talked about in class a little bit to find acceleration. So in this case, we're going to use it to find mass. So in this case, capital M is mass of the sun. So I rearrange that algebraically to get the mass all by itself, which is equal to the gravitational acceleration times r squared, all that divided by the gravitational constant. That gets me the mass of the sun of 1.99 times 10 to the 30th kilograms, which within rounding is exactly the mass of the sun. So pretty cool. It should work for all planets, actually, around the Earth. And again, this is a way we can detect the mass of stars where we have extrasolar planets. And if you want more information about that, you can talk to me, or if you're in an astronomy class, you can certainly talk to your teacher, who I think is Mr. McCullough, about that. Thanks.